Picture something the size of a grand piano, falling out of a clear morning sky. No sirens, no warning, just a small dark shape tumbling through the clouds, quiet enough that a farmer standing in his field might mistake it for a bird. Then it touches the ground, and Texas stops existing. Not an exaggeration written for effect. 60 kilograms of the right kind of matter, striking the Earth at the right speed, releases more energy than every nuclear weapon ever detonated on this planet combined, multiplied 1,000 times over. A single piece of furniture-sized rock, if it were made of the right stuff, could outperform the largest bomb humanity has ever built by a factor of 5,000. The strange part is that nothing about this object would look unusual before impact. In the vacuum of space, it would drift silently among a billion identical-looking rocks, indistinguishable from any ordinary chunk of stone tumbling through the dark. It would not glow. It would not hum. It would carry no warning label written across the cosmos. Only physics would know the difference, and physics does not send memos. We are talking about antimatter meteors. Objects that may or may not exist, built from a substance that should have erased the entire universe before a single star had the chance to ignite. Tonight, we are going to ask an uncomfortable question. What if some of the rocks quietly falling toward Earth right now are not rocks at all, but bombs built by the universe itself, disguised as stone? By the end of this journey, you will understand why physicists have spent a century hunting for something that appears to be almost entirely, suspiciously, unfairly absent from the cosmos. And you will understand why a dead star 800 light-years away, one that refused to behave the way physics expected it to, may hold the answer to where all of it went. Ordinary matter built everything you have ever touched. Your hands, your coffee cup, the chair beneath you, the planet under your feet. All of it obeys one simple rule book, made of protons, neutrons, and electrons. Oh! And you will not love any of these worlds. Antimatter follows an almost identical rulebook, with one devastating exception. The moment it meets ordinary matter, both substances vanish in a flash of pure energy. No debris, no leftover dust, just light and a great deal of it. Physicists discovered this mirror universe substance decades ago, and ever since, one question has haunted the field. If the early universe created equal parts matter and antimatter, as our best theories insist it must have, then the two should have annihilated each other completely the instant they touched. Stars should never have formed. Galaxies should never have condensed. You should not be sitting here reading this sentence. Something broke the symmetry. For every billion antimatter particles born in the first fraction of a second after the Big Bang, roughly 1,000,000,001 particles of ordinary matter came into existence instead. That single extra particle in a billion is the entire reason a universe of stars, planets, and thinking creatures exists at all. Scientists still do not know what caused that tiny imbalance. It remains one of the deepest unsolved riddles in physics, hiding in plain sight inside every atom you are made of. Today, the only antimatter we reliably produce comes from human ingenuity rather than cosmic leftovers. Particle accelerators at facilities like CERN manufacture tiny quantities of it under carefully controlled conditions. Even hospitals keep miniature versions of these machines running quietly in basements, generating positrons for PET scans that peer inside your body. But these are drops in a bucket, manufactured grams next to a universe that, by rights, should be swimming in the stuff. Absence, though, is not the same thing as proof. Just because we rarely detect antimatter drifting through space does not mean pockets of it never survived the chaos of creation. And that possibility is where our story truly begins. Strange as it sounds, you have almost certainly stood next to manufactured antimatter without ever knowing it. Hospitals around the world run a diagnostic procedure called positron emission tomography, or PET, and the name is not a marketing gimmick. Patients receive a mildly radioactive tracer that decays by emitting positrons, a very same antimatter particle Carl Anderson first spotted curving through his cloud chamber in 1932. Each positron travels only a few millimeters through tissue before colliding with an ordinary electron, annihilating in a tiny, precise detectable flash of gamma rays that a ring of sensors uses to build a three-dimensional map of activity inside the body. Doctors have relied on this technique since the 1970s to spot cancers, study brain activity, and evaluate heart function, all thanks to controlled, miniature annihilation events happening safely inside patients every single day. The machines that generate these positrons are, in the strictest sense, small particle accelerators, cousins of the enormous rings at CERN, shrunk down to fit inside a hospital basement, and tuned to produce antimatter in doses too small and too short-lived to pose any danger. This is worth sitting with for a moment, because it reframes everything that follows. Antimatter is not some forbidden substance locked away exclusively in the world's most extreme physics laboratories. In carefully measured amounts, it has quietly become a routine medical tool, produced on demand, used safely, and disposed of within minutes through natural annihilation. The same substance capable, in theory, of erasing a state the size of Texas is also, in a different context and a vastly smaller quantity, helping radiologists spot tumors before they spread. The gulf between those two scenarios comes down entirely to scale. A PET scan uses a quantity of antimatter measured in a fraction of a gram, spread out and consumed harmlessly over the course of an appointment. Our hypothetical meteor carried 60 kilograms, surviving all the way to the ground. Antimatter, in other words, is not inherently apocalyptic. Quantity is the only variable standing between a diagnostic tool and a weapon capable of devastating a continent. And that single fact should make the search for naturally occurring antimatter feel considerably more urgent than it otherwise might. Before we go chasing antimatter across the galaxy, it turns out a small, harmless amount has been quietly orbiting our own planet the entire time. In 2011, data collected by the Geminga satellite, a cosmic ray detector launched by a collaboration of Italian, Russian, German, and Swedish researchers, confirmed something remarkable. A thin band of antiprotons trapped within Earth's own Van Allen radiation belts, the same donut-shaped regions of charged particles held in place by our planet's magnetic field. These antiprotons are not primordial leftovers from the Big Bang, nor are they visitors from some distant anti-star system. They form locally and continuously, produced when high-energy cosmic rays from deep space slam into the upper layers of Earth's atmosphere, occasionally generating antiproton-antitronon pairs as a byproduct of the collision. Earth's magnetic field then captures a small fraction of these newly created antitronons before they can annihilate, trapping them in stable orbits within the inner Van Allen belt, sometimes for weeks or months at a time, before they eventually collide with atmospheric particles and disappear. When the quantities involved are almost comically small, estimated at roughly 1 antiproton for every few hundred cubic centimeters, meaning the entire trapped population across Earth's magnetosphere adds up to something on the order of micrograms at most, nowhere near enough to register as a meaningful safety concern for satellites or astronauts passing through the region. But the discovery mattered scientifically for an entirely different reason. It proved that even a planet as ordinary as Earth naturally generates and briefly stores measurable quantities of antimatter as a routine side effect of simply existing inside a universe full of cosmic radiation. The first aeration of this element of heart, that single fact, reframes the entire question this documentary has been asking. Antimatter is not some impossibly rare substance confined to distant exotic stars and multi-billion-dollar particle accelerators. It is being manufactured in small but measurable quantities right now in the space immediately surrounding your own planet, produced by nothing more exotic than ordinary cosmic rays colliding with ordinary atmosphere. The real mystery was never whether antimatter can exist in nature. It clearly does, constantly, in small pockets scattered from Earth's own backyard all the way out to dying stars 800 light-years distant. The mystery has always been why there isn't dramatically more of it. Flip a coin enough times, and eventually you will hit a run of nothing but heads. Not because the coin is changed, but because probability guarantees clusters exist inside chaos, given enough attempts. The infant universe flipped its own coin trillions upon trillions of times as raw energy called into the first particles of matter and antimatter. Most regions of that primordial soup landed close to the average, tipping only slightly toward matter, the imbalance responsible for the universe we know. But statistics rarely behave with perfect uniformity across every corner of a system this vast. In certain pockets, purely by chance, antimatter could have clumped together in greater concentrations than its surroundings, and gravity does not discriminate between the two. It pulls whatever mass happens to be nearby, matter or antimatter, drawing it inward until stars ignite. If such a pocket grew large enough, before it had the chance to collide with its opposite number, it would not annihilate away into background radiation. It would become a solar system, an entire star, its planets, its asteroid belts, built from mirror matter instead of the ordinary kind, indistinguishable from any other star system unless you looked extremely closely at the edges where it met the rest of the galaxy. That boundary is the giveaway. Where regular interstellar gas brushes against the outer reaches of an antimatter star system, the two substances would collide and annihilate, producing a telltale flood of gamma radiation, visible from thousands of light years away. Astronomers went looking for exactly that signature, and in 2021, the Fermi Large Area Telescope turned up 14 candidates in our own Milky Way that emit gamma rays consistent with anti-star annihilation. None of them have been confirmed. Pulsars and black holes can mimic the same signal, and ruling out every alternative explanation takes time. But the possibility has not been eliminated either. If even a fraction of those 14 candidates turn out to be genuine anti-stars, the implication is staggering. Roughly one star in every 400,000 across our galaxy might be built from the opposite substance to everything around it, complete with its own planets, its own asteroid belts, and quite possibly its own antimatter meteors drifting through its own version of a solar system. In 1967, Soviet physicist Andrei Sakharov sat down and worked out exactly what conditions the universe would need to satisfy in order to end up with more matter than antimatter. He identified 3 separate requirements, and remarkably, all 3 still shape every serious theory of baryogenesis, the technical term for the process that produced our matter-dominated cosmos more than half a century later. The first condition demanded a process capable of actually converting antimatter into matter, or vice versa, changing what physicists call baryon number. Ordinary particle interactions preserve this quantity perfectly, meaning some exotic, currently unidentified interaction had to exist in the universe's first fraction of a second to nudge the balance even slightly. The second condition required that both charge symmetry and the combined charge parity symmetry be violated, essentially demanding that nature treat left-handed and right-handed versions of particles differently enough to create a genuine, lasting imbalance rather than one that cancels itself back out. We now know this condition is satisfied, thanks to Cronin and Fitch's 1963 discovery of exactly this kind of violation in the weak force. Though, as we will see shortly, the magnitude of that violation turns out to be nowhere near sufficient on its own. The third and final condition required that all of this happen while the universe was out of thermal equilibrium, meaning conditions had to be changing rapidly enough that any imbalance created couldn't simply average back out to zero before it had a chance to matter. Many physicists suspect this condition was satisfied during an extraordinarily brief period in the universe's first instance, when rapid cooling and phase transitions created exactly the kind of chaotic, non-equilibrium environment Sakharov's third rule demanded. Here is the uncomfortable part. Even with all three Sakharov conditions technically satisfied by known physics, the numbers still don't add up. The known violation of charge parity symmetry in the weak force is roughly 10 billion times too small to account for the matter-antimatter imbalance actually observed in our universe. Something else, some undiscovered particle, some unknown interaction, some entirely new physics beyond the current standard model must be doing the vast majority of the heavy lifting. Sakharov handed physicists a precise checklist in 1967. Nearly 6 decades later, we have confirmed 2.5 of his 3 conditions, and the missing half is arguably the single biggest open question in all of fundamental physics. If the known violation in the weak nuclear force is 10 billion times too small to explain why matter won out over antimatter, something else has to be doing the actual work. And physicists have spent decades building competing theories to fill that gap. None of them has been confirmed. All of them remain, for now, educated speculation, dressed up in the language of mathematics. But understanding the leading candidates helps illustrate just how creative this hunt has become. Weptogenesis proposes that the imbalance originated not with ordinary matter particles at all, but with an exotic, extremely heavy cousin of the neutrino. One so massive, it could only have existed briefly in the universe's first fraction of a second before decaying away. If that heavy neutrino decayed slightly more often into matter than antimatter, the theory suggests the resulting imbalance could have later transferred into ordinary matter through separate, already understood particle interactions, effectively laundering an initial asymmetry from an invisible sector of physics into the visible universe we inhabit today. The appeal of leptogenesis lies in its connection to other unsolved puzzles, particularly the mysteriously tiny mass of ordinary neutrinos, suggesting one elegant mechanism might solve 2 mysteries simultaneously. Grand unified theory. Baryogenesis takes a different approach entirely, proposing that at the extraordinarily high energies present in the universe's first instance, the electromagnetic, weak, and strong forces briefly merged into a single, unified force, governed by physics that allowed baryon number itself to change in ways impossible under today's cooler, more differentiated conditions. Certain hypothetical particles predicted by these unified theories, extraordinarily massive and unstable, could have decayed asymmetrically during this early hot phase, seeding the imbalance before the universe cooled enough to separate the forces into the 4 distinct ones we observe today. The catch is that grand unified theories predict other observable consequences, most notably proton decay. And despite decades of increasingly sensitive searches inside detectors built specifically to catch a proton in the act of falling apart, not a single such decay has ever been observed. Electroweak baryogenesis offers a third path, suggesting the imbalance could have formed later, during a more modest and better understood transition, when the electroweak force split into its separate electromagnetic and weak components, an event current physics places at around a trillionth of a second after the Big Bang. This scenario has the advantage of relying on physics we can test far more directly using existing particle accelerators, but calculations using the standard model alone suggest this transition happened too smoothly, without the violent, out-of-equilibrium conditions Sakharov's third rule demands, meaning some additional new particle beyond the standard model would still need to exist to make this version of the story work. Each theory has its champions, its critics, and its own dedicated experiments hunting for supporting evidence. None has yet produced the kind of smoking gun result that would settle the matter. What all three share, tellingly, is a reliance on physics beyond anything currently confirmed, a quiet acknowledgement from the entire field that the standard model, for all its extraordinary successes, is missing at least one chapter. And that chapter happens to be the reason any of us are here to read it. Claiming that 14 candidate anti-stars exist somewhere within our galaxy raises an obvious follow-up question. How would anyone actually distinguish a genuine antimatter star from the dozens of other exotic objects capable of producing similar gamma-ray signals? The answer involves a surprisingly specific process of elimination, one that leans heavily on the exact energy signature analyzing events are expected to produce. When matter and antimatter annihilate directly, the resulting gamma rays carry a very particular, theoretically predictable energy spectrum, dominated by a spike at roughly 511,000 electron volts, corresponding precisely to the rest mass energy of an electron-positron pair. This specific spectral fingerprint gives astronomers something concrete to search for, distinct from the broader, smoother gamma-ray spectra typically produced by pulsars, black holes, or the superheated material surrounding active galactic nuclei. The team responsible for identifying the 14 candidates cross-referenced years of Fermi Large Area Telescope data against exactly this predicted signature, searching for sources whose overall spectral shape matched what an anti-star's boundary annihilation should theoretically produce, while simultaneously ruling out sources with known alternative explanations. That filtering process eliminated the overwhelming majority of gamma-ray sources catalogued by Fermi almost immediately. Known pulsars were excluded based on their characteristic periodic pulsing, a signature no anti-star candidate should display, since the annihilation process, unlike a pulsar's beamed rotation, produces a comparatively steady glow rather than a rhythmic flash. Known supernova remnants were excluded based on their broader, differently shaped spectral profiles. Sources coinciding with catalogued blazars, the extraordinarily energetic cores of distant active galaxies, were excluded based on positional overlap, with objects already well understood through independent observations at other wavelengths. What remained after this careful subtraction process were the 14 unexplained sources whose spectral shape most closely resembled theoretical predictions for anti-star annihilation, without a confirmed conventional explanation available to rule them out. Crucially, none of the 14 have been proven to be anti-stars. They remain candidates precisely because ruling out every conceivable alternative explanation, however unlikely, requires additional follow-up observations that haven't yet been completed for each individual source. Future gamma-ray observatories, offering finer spectral resolution than Fermi currently provides, should be capable of confirming or eliminating each candidate with far greater confidence, turning today's tentative list of 14 into either a confirmed discovery of the first antimatter stars ever found, or, just as scientifically valuable, a definitive list of exotic, conventional objects that happen to briefly resemble something far stranger. Long before Fermi's telescope existed, one man already suspected something was hiding among the stars. Vladimir Rozinsky, a Russian-American physicist, began speculating about antimatter meteors back in 1940, barely a decade after antimatter had even been confirmed to exist as a concept. His reasoning was elegantly simple. Somewhere in the galaxy's long history, our solar system likely passed close to an antimatter star system at some point in its 4.5 billion-year orbit around the galactic center. Gravitational interactions during that near miss could have flung a handful of outlying antimatter objects loose from their original orbits, sending them drifting through interstellar space on new, unpredictable paths. Given enough time and enough passing stars, some of those wandering fragments could plausibly end up crossing paths with Earth. Crucially, these objects could never have formed inside our own solar system. The instant any antimatter particle encountered the ordinary matter already present here, in the solar wind, the dust, the debris left over from planetary formation, it would annihilate almost instantly. Any antimatter meteor reaching us would have to be a visitor from somewhere else entirely, a survivor of an impossibly long and lonely journey through the emptiness between stars. Soon after Rojansky raised the idea, American astronomer Lincoln LaPaz picked up the thread and began wondering whether any of Earth's known impact craters might already carry the fingerprints of such a collision. His curiosity set the stage for a question that has quietly persisted in the background of astrophysics for over 80 years. If one of these objects ever did hit us, would we even recognize the wreckage for what it was? To answer that, we first need to understand exactly what happens when an antimatter object meets an atmosphere built entirely of the thing it is designed to destroy. Every ordinary meteor faces the same brutal filter on its way down. Friction against the atmosphere generates enormous heat, and depending on size, the object either burns away completely or survives long enough to strike the ground. An antimatter meteor faces something far worse. It does not just burn. Every single particle of air it touches annihilates an equal quantity of its own mass, converting both into pure energy, according to Einstein's famous equation, doubled, because both the meteor and the atmosphere are being consumed in the exchange. Let's actually run the numbers, because the scale of what follows is difficult to grasp in the abstract. 90% of Earth's atmosphere sits within the lowest 16 kilometers above the surface, clinging close to the planet under the pull of gravity. Adding up the total mass of air packed into a narrow 1 meter by 1 meter column, stretching from the edge of space down to the ground, gives a figure of roughly 10,000 kilograms. Assume an antimatter meteor built from the same average density as a typical stony meteorite, somewhere around 3,400 kilograms per cubic meter. Run the balance between how much surface area a given size exposes to the atmosphere against how much total mass it carries, and a sweet spot emerges. A cube measuring 3 meters on each side, 27 cubic meters in total, works out to a mass of roughly 92,000 kilograms. On the way down, it would annihilate against approximately 91,000 kilograms of atmosphere, leaving a remainder of about 60 kilograms still intact by the time it reaches the ground. 60 kilograms is nothing. It is lighter than most adult humans, roughly the mass of a large grand piano. And yet, plugging that number into E equals mc squared, then doubling the result to account for the equivalent mass of atmosphere destroyed alongside it, produces an energy release of over 100 quintillion joules. For comparison, a single 1 megaton nuclear warhead releases about 4 quadrillion joules. Even the largest nuclear weapon ever detonated by humanity, the Soviet Tsar Bomba, at 50 megatons, released roughly 200 quadrillion joules, and our 60-kilogram grand piano of antimatter still outproduces it 5,000 times over. When Tsar Bomba exploded in 1961, it leveled towns 55 kilometers away, cracked windows in Norway and Finland over 1,000 kilometers distant, and lit the sky bright enough to be seen from 1,000 kilometers off. Our imaginary antimatter meteor, smaller than a car, would make that historic blast look like a lit match. Drop something that size into the middle of Texas, and the center of the state simply stops existing. What remains would not resemble a disaster zone so much as a fresh crater the size of a small country, surrounded by devastation stretching across state lines. And remember, this accounting only covers the 60 kilograms that survived to strike the ground. Factor in the 91,000 kilograms annihilated higher up in the atmosphere, and the true blast radius balloons outward. Some of that upper energy would vent harmlessly into space, but enough would radiate downward and outward to threaten not just one state, but potentially an entire country. All of that devastation, worth repeating, from an object roughly the size of a family car. The 3-meter cube used in our earlier calculation was chosen deliberately, sitting near the mathematical sweet spot where surface area and volume balance out most efficiently for delivering mass to the ground. But nature rarely hands us objects tuned to convenient sweet spots, so it's worth asking what happens at other sizes, because the answer is not simply more damage. Proportionally, shrink the object down towards sand grain size, roughly comparable to the 100 tons of natural micrometeorite dust that bombards Earth every single day without anyone noticing. And an antimatter version would never survive contact with the upper atmosphere at all. Surface area dominates completely at that scale, meaning the entire object annihilates within the first few kilometers of atmospheric entry, releasing its energy so high above the ground that almost none of the resulting blast would even register at the surface. Antimatter dust, in other words, poses effectively zero danger, which is a small mercy given how much of it may already be raining down on us in quantities too small to distinguish from ordinary micrometeorites. Scale upward instead, towards something car-sized or slightly larger, roughly comparable to the object that exploded over Chelyabinsk, Russia in 2013, and the picture changes dramatically. That real ordinary matter event released energy equivalent to roughly 500 kilotons of TNT, injuring over 1,000 people primarily for shattered glass and shockwave damage, despite the meteor itself never actually reaching the ground intact. An antimatter object of comparable size, using the same balance of surviving mass against atmospheric annihilation calculated earlier, would not merely shatter windows across a city, it would remove the city. Push the scale further still, toward the roughly 10 to 15 kilometer wide impactor believed responsible for ending the age of dinosaurs 66 million years ago. An event that released energy equivalent to billions of Hiroshima bombs and triggered a mass extinction event still visible in the geological record today. And an antimatter equivalent moves from catastrophic into genuinely planet-threatening territory. At that scale, the total energy release would not simply devastate a region or a continent. It would plausibly disrupt the crust itself, trigger effects capable of altering the planet's climate for geological timescales, and, as our cold open suggested at the very start of this journey, raise legitimate questions about whether Earth would remain recognizably intact afterward. One more variable deserves mention: where the object actually lands. Roughly 70% of Earth's surface is ocean, and striking water rather than solid ground changes the physics considerably. Water is denser than air, but far less resistant than rock, meaning an antimatter object would annihilate somewhat differently on impact, converting a significant portion of its energy into a colossal steam explosion and potential tsunami generation, rather than a single concentrated ground-level blast. Devastating either way, but the specific mechanism and the specific populations placed at risk would shift considerably depending on whether the ocean or the continents happen to be waiting underneath. Let's walk through what those final moments would actually look like, purely as a thought experiment, grounded in the physics we've already established. 90 seconds before impact, our 60 kHz survivor is still roughly 30 kilometers up, deep inside the thickest part of the atmosphere, and already annihilating against air molecules at a ferocious rate. From the ground, this would not look like an ordinary meteor's brief, elegant streak. It would look like a second sun ignited somewhere overhead, a point of light climbing rapidly in brightness as the annihilation rate increased with altitude and atmospheric density. 30 seconds before impact, anyone within visual range would already be looking away instinctively, the way you flinch from an arc welder or a camera flash held too close. Except this light source would be growing brighter by the second, rather than fading. Sound would lag dramatically behind sight, exactly the way thunder trails lightning, meaning the visual spectacle would unfold in eerie silence for several more seconds, before the first wave of displaced air finally caught up. 10 seconds out, most of the object's original mass has already annihilated in the layers above, and what remains is falling through the final, densest stretch of atmosphere at a velocity still measured in tens of kilometers per second. The light by this point would be brighter than the actual sun to anyone watching from within several hundred kilometers, a genuinely dangerous flash capable of causing retinal damage to anyone who hadn't already looked away. And then, impact. Not a crater in the traditional sense, since so little physical material would remain to leave one, but a blinding release of energy at ground level, converting the immediate area and everything in it directly into vapor and plasma within a fraction of a second. The shockwave would radiate outward from that point at speeds initially exceeding the speed of sound, flattening structures, forests, and terrain across a radius stretching hundreds of kilometers, considerably farther than Tsar Bomba's most severe damage zone, before finally slowing to something resembling an ordinary, if still catastrophic, blast wave at the outer fringes. Thermal radiation would arrive first, an intense pulse of heat, capable of igniting fires and causing severe burns across an enormous radius, followed seconds to minutes later by the mechanical shock wave itself, and finally, over the following hours, a rain of debris and dust lofted high into the stratosphere, some of it circling the globe before eventually settling, contributing to short-term climate disruption, not unlike, though considerably smaller in scale then, the aftermath researchers associate with the asteroid impact that ended the age of dinosaurs. This entire sequence, from first detection to final settling debris, would unfold across less than 2 minutes for the initial blast, followed by weeks or months of secondary atmospheric effects. 90 seconds separating an ordinary sky from a permanently altered map. It is precisely this speed, this near-total absence of meaningful warning time, that makes the scenario worth taking seriously as a thought experiment, even while every calculation covered earlier in this documentary suggests the actual odds of it ever occurring remain vanishingly small. Given numbers like that, the natural next question is whether one of these things could already be lurking among the 40,000 near-Earth asteroids that NASA currently tracks, The reassuring answer is almost certainly not. And the reason comes down to something surprisingly mundane. Space is dirtier than people assume. Even the vast emptiness between stars contains trace amounts of dust and gas, scattered thinly but persistently across every light year. An antimatter object drifting through that environment would collide with tiny particles constantly, and each collision would annihilate a small portion of its mass. Calculations suggest that an antimatter asteroid traveling through the interstellar medium would have a survival window of roughly 300 years before it accumulated enough microscopic impacts to disintegrate entirely into gamma radiation. 300 years is a blink of an eye set against the timescales this story usually deals in. Our solar system last passed close enough to brush against another star roughly 70,000 years ago, an encounter with the aptly named Schultz's star. For an antimatter meteor to have survived that entire journey unscathed, dodging every asteroid, avoiding every stray particle of interstellar dust, and still arriving intact within our solar system today, it would need almost impossible luck stretched across tens of thousands of years. The same logic rules out antimatter comets sneaking through on long interstellar trajectories. Smaller ones would burn away to nothing before reaching us. Larger ones would announce their presence loudly and continuously, radiating a steady stream of gamma rays as they collided with interstellar dust along their entire route, glowing like a beacon visible to modern telescopes. No such object has ever been spotted, sparkling its way silently through the outer solar system. So the honest conclusion is reassuring, even if it required imagining apocalyptic scenarios to arrive there. Antimatter meteors, should they exist at all, almost certainly cannot survive long enough to reach Earth intact. We are, in all likelihood, quite safe, though in all likelihood is doing some heavy lifting in that sentence, because history has already handed us one genuinely strange, unsolved mystery that briefly made scientists wonder. Not every antimatter meteor drifting through the solar system would necessarily aim itself at Earth, and it's worth briefly considering what a strike elsewhere in our neighborhood might reveal, if only because the answer highlights just how uniquely well-suited our own planet is to hiding the evidence. The Moon offers the clearest comparison. With no atmosphere whatsoever to trigger the kind of gradual annihilation cascade calculated earlier, an antimatter object approaching the lunar surface would strike essentially at full mass, converting its entire bulk into energy in a single, instantaneous event rather than the staged atmospheric burn a planet with air would produce. A meteor of the same 3-meter, 92,000 kilogram scale used in our earlier Earth calculation would release energy equivalent to annihilating that full mass rather than the mere 60-kilogram remainder that would have survived Earth's atmosphere. A difference measured in the thousands. Lunar seismometers, had any been active nearby, would have registered an event unmistakably different from any ordinary impact in the Moon's geological record, likely visible even from Earth as a brief, brilliant flash. Mars presents a middle ground. Its atmosphere present, but only about 1% as dense as Earth's, meaning an antimatter object would face dramatically less resistance on the way down, annihilating a smaller fraction of its total mass before reaching the surface and striking with far more of its original bulk intact, compared to an equivalent object entering Earth's much thicker atmosphere. Given NASA's growing fleet of Mars orbiters and surface rovers, a strike of even modest size, occurring during the modern era of Mars exploration, would likely register across multiple instruments simultaneously, from orbital cameras capturing the flash to seismometers detecting the resulting groundquake. None of this changes the underlying physics established earlier regarding how unlikely any of these scenarios actually are. What it does illustrate is a subtler point about detection. Earth's own atmosphere, The very feature that makes our planet capable of supporting life also happens to be remarkably efficient at consuming the physical evidence an antimatter impact would otherwise leave behind, annihilating the vast majority of any such object before it ever reaches a surface where geologists could later examine the debris. A crater on the airless moon would preserve far more diagnostic evidence of an antimatter strike than an equivalent event occurring here on Earth. An odd reminder that the same atmosphere protecting us from countless smaller, ordinary meteors might also be quietly erasing the clearest evidence we'd ever get of the rarer, far stranger kind. On a June morning in 1908, in a remote stretch of Siberian forest near the Tunguska River, the sky tore open. Witnesses, more than 30 kilometers away, reported a flash brighter than the sun, followed by a shock wave and a roar of thunder that rattled windows and knocked people off their feet. Above the forest, something detonated with such force that it flattened trees across an area of roughly 2,000 square kilometers, laying them down in neat, radial patterns like fallen dominoes pointed away from the blast. Because of the region's remoteness, no scientific expedition reached the site until 1927, nearly 2 decades later. By then, the destruction was still unmistakable, an entire forest lying in ruins, with no crater, no obvious impact site, and almost no physical trace of whatever caused it, beyond a scattering of microscopic particles embedded in the soil. Naturally, an event this violent and this mysterious invited speculation, and antimatter was floated as one possible culprit during the decades that followed. The scenario fit the pattern almost too well. An object explodes with tremendous force, causes catastrophic destruction, and leaves behind virtually no debris. If a meteor had annihilated in the atmosphere before reaching the ground, exactly the way our earlier calculations described, the physical evidence left behind would indeed be minimal. Modern reanalysis using computer modeling and comparisons against nuclear test data has only sharpened the picture. Researchers matching the pattern of flattened trees against blast simulations now estimate the Tunguska event released energy somewhere between 10 and 15 megatons, comparable to roughly 1,000 Hiroshima bombs, entirely from an object believed to have measured only around 60 meters across before it detonated in the air. Sediment cores and soil samples collected decades later did eventually turn up trace amounts of iridium and other markers consistent with an ordinary stony or icy body, quietly closing off most of the exotic explanations that once circulated. Yet the sheer disproportion between the object's modest size and the almost unbelievable scale of destruction it caused is exactly the kind of detail that keeps alternative theories alive in public imagination, long after the scientific debate has effectively settled elsewhere. To be clear, the scientific consensus today does not support an antimatter explanation for Tunguska. A stony or icy meteor exploding in the atmosphere, a phenomenon known as an airburst, explains the observed damage far more comfortably without requiring exotic feats. But the fact that antimatter was ever seriously discussed as a candidate shows how naturally this idea slots into real unsolved mysteries, and how thin the line can look between rigorous physics and genuinely unsettling speculation. We know what Tunguska probably wasn't. What we still don't fully know is why the universe seems to have almost none of the substance capable of causing it in the first place. To chase that answer, we need to leave meteors behind entirely and step into a laboratory built to catch antimatter red-handed, misbehaving. Given everything discussed so far, it's worth asking a practical question. If an antimatter meteor really were approaching Earth, would our current detection systems catch it in time? Or would we only find out the way Tungus's witnesses did, standing beneath a sky that had already torn itself open. Existing planetary defense systems, including NASA's Center for Near-Earth Object Studies, primarily rely on optical telescopes, scanning for reflected sunlight bouncing off approaching objects. This method works reasonably well for detecting large asteroids well in advance, but it carries an important limitation relevant to our story. Reflected light reveals nothing whatsoever about internal composition. An antimatter meteor would look, sound, and reflect light exactly like an ordinary chunk of stone or ice, right up until the moment it began interacting with something. That moment would actually come earlier than impact, and this is where the story gets genuinely interesting. Long before reaching the ground, an antimatter object would have already encountered the outermost wisps of Earth's exosphere and the solar wind streaming past our planet, triggering small-scale annihilation events and producing gamma radiation as a byproduct. Orbiting gamma-ray observatories, similar in principle to the instruments that eventually caught Geminga's signal, could theoretically detect this telltale signature during the final seconds or minutes of approach, offering a warning that, while agonizingly brief, would be considerably better than nothing. The honest, unglamorous answer is that no purpose-built early warning system for incoming antimatter currently exists, because the scientific community remains unconvinced any such objects are out there to warn against in the first place. Every dollar and every telescope hour committed to ordinary defense is currently allocated toward ordinary asteroids and comets, a threat that, unlike antimatter meteors, we know for certain is real, recurring, and statistically inevitable over long enough timescales. Should convincing evidence for surviving antimatter meteors ever emerge, retrofitting existing gamma-ray observatories to watch for exactly this kind of last-second signature would likely be one of the fastest, cheapest defensive upgrades available, precisely because much of the necessary hardware, originally built to study distant pulsars like Geminga, is already in orbit and already pointed at the sky. Everything around you, your skin, your phone, the walls of the room you're sitting in, is built from the same three ingredients: protons, neutrons, and electrons. Look toward Mars, same ingredients. Look toward the Andromeda Galaxy, 2.5 million light-years distant. Same ingredients again. Scan halfway across the observable universe, and the recipe never changes. For once in physics, the deepest mystery is not something strange we found, but something ordinary we expected to find and largely didn't. A universe equally stuffed with antimatter. The story of how we first caught antimatter in the act begins in 1932, inside a cloud chamber at Caltech. Physicist Carl Anderson had built the device to study cosmic rays, high-energy particles raining down from space, by placing the chamber inside a magnetic field that would bend the path of any charged particle passing through, curving it according to mass and charge. What Anderson found included particles curving exactly the way negatively charged electrons should. But mixed among them were positively charged particles, bending along paths that matched an electron's mass precisely, despite carrying the opposite charge entirely. These impossible particles came to be called positrons, the antimatter counterpart to the electron, and the discovery earned Anderson a Nobel Prize in 1936. Remarkably, though, theory had beaten observation to the punch. British physicist Paul Dirac had already predicted the existence of exactly this particle back in 1928, 4 years before Anderson's chamber caught one on film. Dirac had been working to reconcile electrons with the framework of special relativity, and the mathematics simply refused to describe electrons without also describing a mirror image partner carrying the opposite charge. Nature, it turned out, had been hiding the answer inside an equation the whole time. Electrons were only the beginning. Quarks, the tiny building blocks that combine to form protons and neutrons, carry their own antimatter counterparts too. Antiquarks bind together into antiprotons and antineutrons, which in turn can capture positrons to build complete antiatoms. In principle, you could construct an entire planet out of nothing but antimatter, and viewed from the outside, it would look almost indistinguishable from any ordinary world. Almost. That single word carries the weight of the entire mystery. Because if antimatter behaved in every conceivable way exactly like ordinary matter, there would be no explanation left for why our universe overwhelmingly favors one over the other. Carl Anderson's name is the one history remembers, but the 1932 discovery of the positron was closer to a photo finish than most textbooks let on. Across the Atlantic, at Cambridge University, physicist Patrick Blackett had been running remarkably similar cloud chamber experiments, and by some accounts, had already captured images of positron tracks before Anderson published his own results. Blackett, working alongside Italian physicist Giuseppe Occhialini, wanted to be absolutely certain before announcing anything, cross-checking the unusual tracks against every conventional explanation his team could think of, verifying instrument calibration and ruling out contamination or artifacts, a level of caution that, while scientifically admirable, cost him the priority of publication. Anderson, working independently and unaware of Blackett's progress, published first, and the Nobel Committee awarded him the prize in 1936, largely on that basis. To their credit, both men handled the outcome with unusual grace. Blackett would go on to win his own Nobel Prize in 1948, recognized for his broader contributions to cloud chamber physics and cosmic ray research, including the very techniques that had nearly delivered him credit for antimatter's discovery 4 years earlier. Anderson, for his part, always acknowledged Blackett and Occhialini's parallel rigorously verified work in his own later writings, and the wider physics community has long treated the positron's discovery as something closer to a shared achievement than a solitary triumph, even if only one name typically appears in the history books. The episode carries a small but genuinely useful lesson buried inside it. Being first to publish and being first to discover are not always the same event, and the margins separating them can come down to something as unglamorous as how thoroughly a research team insists on checking its own results before going public. Antimatter's discovery, in other words, was contested, careful, and nearly simultaneous from its very first moment. A fitting beginning for a substance that has spent every decade since refusing to give up its secrets easily. Physicists have spent close to a century searching for meaningful cracks between matter and antimatter, because finding one is the only way to explain why we exist at all. Under electromagnetic forces, the two behave identically, apart from their opposite charge, exactly as Anderson observed inside his cloud chamber. Their masses match to extraordinary precision in every experiment ever run. For decades, the search for asymmetry kept coming back empty. Then, in the 1950s and 1960s, physicists studying the weak nuclear force stumbled onto something genuinely strange. Ordinary particles interact with the weak force only if they display a property called left-handedness, while antiparticles interact with it only if they display the opposite, right-handedness. Handedness, formerly known as chiality, is a subtle concept, loosely comparable to whether a particle spins in the same direction it travels or against it. Stranger still, right-handed antiparticles were found to experience the weak force at a slightly different strength than left-handed ordinary particles do. meaning radioactive decay processes in ordinary atomic nuclei play out with marginally different odds than the mirror image decay in antinuclei. This asymmetry was confirmed experimentally in 1963 by James Cronin and Val Fitch at Princeton, work that later earned its own Nobel Prize. For a brief hopeful moment, physicists wondered whether this single discovery might explain the entire cosmic imbalance between matter and antimatter. Run the numbers though, and the math falls painfully short. The weak force asymmetry is real, but nowhere near large enough to account for a universe built almost entirely out of one substance and almost none of the other. Attention then shifted to the strong nuclear force, the interaction that binds quarks together inside protons and neutrons. Theoretical models predicted a similar handedness-based asymmetry should show up there too. But every experiment run to date has found the strong force treating matter and antimatter with total, boring equality. No asymmetry, no clue, just one more dead end in a search that has consumed careers. That leaves gravity, the fourth and final fundamental force, and the one physicists have been most reluctant to suspect of playing favorites. According to legend, Galileo once dropped objects of different materials from the top of the Leaning Tower of Pisa and watched them strike the ground simultaneously, demonstrating that gravitational acceleration does not care what an object is made of. Isaac Newton later formalized the idea mathematically, showing that gravitational pull depends only on mass and distance, never on any other property of the falling object. This principle, known as the equivalence principle, forms one of the load-bearing pillars of Einstein's general relativity, arguably our most successful scientific theory in history. Hungarian physicist Loran Avos spent decades around the turn of the 20th century refining exactly this idea, using an extraordinarily sensitive torsion balance to compare the gravitational and inertial mass of different materials, confirming their equivalence to within 1 part in 100 million, a level of precision that later experiments, including satellite-based tests in the 2010s, pushed even further, down to roughly 1 part in 100 trillion. Every single material ever tested, from wood to platinum to exotic laboratory alloys, has obeyed the equivalence principle without exception. Antimatter, until Alpha's experiment, was simply the one substance nobody had ever been able to test directly. But physics is an experimental discipline at its core, and no assumption survives forever on reputation alone. Nobody had ever actually measured how gravity treats antimatter directly, and a handful of speculative papers had floated the tantalizing possibility that dark matter and dark energy, two of the universe's most persistent unsolved puzzles, might become easier to explain if antimatter carried a negative gravitational charge. In plainer terms, what if antimatter falls up instead of down? That question sent researchers at CERN chasing an experiment of extraordinary delicacy. Multiple teams took up the challenge, including projects named Aegis, GBAR, and Alpha. The Alpha collaboration published the results that concern us here in the journal Nature, and the sheer engineering required to obtain them deserves a moment of appreciation before we get to the numbers. The process begins with a beam of several million positrons per second, produced by a radioactive sodium isotope. Nearly all of them annihilate immediately upon contact with ordinary matter inside the apparatus, flashing briefly into light before disappearing. A small surviving fraction gets guided through the machine, cooled using low-pressure gases, and captured within precisely tuned electric and magnetic fields. Positrons alone, though, are far too light and far too sensitive to stray electromagnetic noise to measure gravity's effect on them directly. The tiny gravitational pull acting on a single positron would be swamped instantly by even minuscule fluctuations in the surrounding fields. The solution was to merge those trapped positrons with a separate supply of antiprotons, produced by firing ordinary protons at a metal target at tremendous speed, forming neutral anti-hydrogen atoms in the process. Being electrically neutral, these anti-hydrogen atoms are far less vulnerable to electromagnetic interference, making them the perfect candidate for a gravity test. Trapped by careful arrangements of external magnetic fields, inside a chamber so close to a perfect vacuum that it contains only about 200,000 atoms of ordinary gas per cubic centimeter. Compared to 20 quintillion atoms in a typical breath of air, the anti-hydrogen atoms can drift, essentially undisturbed, for minutes at a time. Slowly weakening the vertical magnetic fields that hold the anti-hydrogen atoms in place allows them to drift free, escaping either upward through the top of the chamber or downward through the bottom, where they strike the apparatus, annihilate, and release a brief pulse of light. If gravity pulls antimatter downward the same way it pulls ordinary matter, more atoms should escape through the bottom. If gravity somehow repels antimatter upward, the opposite pattern should emerge instead. Simulations run ahead of time predicted the outcome under each scenario. Normal downward gravity would send roughly 85% of atoms escaping through the bottom of the chamber. Reversed, upward pulling gravity would flip that figure to only about 20% escaping downward. A universe with no gravitational effect at all on antimatter would produce something close to an even 55% split, with the small deviation from an exact 50% explained by minor asymmetries built into the physical apparatus itself. Running the actual experiment, the Alpha team found that roughly 75% of anti-hydrogen atoms escaped through the bottom of the chamber, a clear, unmistakable preference for downward motion. Ordinary gravity, it appears, pulls antimatter down exactly the way it pulls everything else. To strengthen the result, the team repeated the procedure across a range of deliberately applied magnetic biases, each one nudging the anti-hydrogen atoms slightly upward or downward with an artificial force calibrated in fractions of Earth's gravity. Plotting the results against predictions for several competing gravitational models produced a clear match with the curve representing ordinary, unmodified gravity. The best fit acceleration came out at roughly 75% of standard gravitational strength, though accounting for every source of experimental uncertainty widened that estimate enough that a full 100% match with ordinary gravity remains comfortably consistent with the data. Antimatter, in other words, does not fall up. Speculative theories built on that premise have effectively been ruled out. Future refinements of the experiment will narrow the precision further, but the headline conclusion already stands. Gravity treats antimatter and matter the same way. The only fundamental force found to treat them differently, even slightly, remains the weak nuclear force, and its contribution is nowhere near large enough to explain why our universe is so lopsided. So the search for a meaningful asymmetry continues. Somewhere, either a new force or a new particle is still waiting to be discovered, or the universe's overwhelming preference for matter over antimatter really is nothing more than an extraordinary cosmic coincidence. Neither answer feels entirely satisfying, but while physicists keep chasing that mystery in laboratories on Earth, something else has been quietly proving that antimatter is not confined to CERN's experimental chambers at all. 800 light-years away, a dead star has been manufacturing the stuff for roughly 350,000 years, and it took astronomers decades just to figure out what they were looking at. The Alpha collaboration's gravity result understandably grabbed headlines, but it represents only one branch of a much broader effort at CERN to hunt down a conceivable difference between matter and antimatter, and understanding its neighbors helps put the achievement in proper context. The base collaboration short for baryon-antibaryon symmetry experiment, took a different approach entirely, focusing not on gravity, but on comparing the charge-to-mass ratio of protons against antiprotons with almost unimaginable precision. Trapping individual antiprotons in a device called a penning trap for extended periods, sometimes for over a year at a stretch. Base researchers measured this ratio to better than 1 part in a trillion, finding it to be identical between matter and antimatter within that staggering margin of error. If any asymmetry exists here at all, it is hiding at a level of precision beyond anything current instruments can detect. The Astrum collaboration pursued yet another angle, focusing on trapping antihydrogen atoms for extended durations and studying their internal atomic structure. Comparing the exact wavelengths of light absorbed and emitted by antihydrogen against the extraordinarily well-measured spectral lines of ordinary hydrogen. Once again, no meaningful difference has ever turned up. Antihydrogen's spectral fingerprint matches ordinary hydrogens to remarkable precision, reinforcing the same frustrating pattern seen throughout this entire field. Every single property physicists have managed to measure comes back identical, except for that one small, stubborn crack in the weak nuclear force. A fourth effort, G-bar, short for gravitational behavior of antihydrogen at rest, takes a complementary approach to alpha's gravity measurement, aiming to drop antihydrogen atoms that are essentially motionless, cooled to extremely low temperatures before release, in order to measure gravitational acceleration with even greater precision than alpha's already impressive result. Multiple independent teams, converging on the same basic question from different experimental angles, is precisely how good science is supposed to work. If gravity really does treat antimatter identically to matter, as alpha's data strongly suggests, G-bar's independent confirmation, using an entirely different experimental method, would put that conclusion beyond reasonable doubt. Taken together, these 4 experiments represent one of the most thorough, most expensive, and most patient searches for a single crack in the laws of physics ever assembled by humanity. And so far, every single one of them has come back with the same disappointing, fascinating answer. Antimatter really does behave almost exactly like matter, in every way we know how to measure, except for the one violation that isn't nearly large enough to explain why we exist. Whatever finally solves the mystery of cosmic baryon asymmetry, it likely lies somewhere these 4 experiments haven't yet thought to look. In 1972, NASA's Small Astronomy Satellite 2 picked up an unexplained source of gamma radiation drifting somewhere within the Geminga constellation. The technology of the era could only narrow the source down to a broad patch of sky, leaving its exact origin a mystery for years. Italian physicist Giovanni Bignami, who would go on to dedicate much of his career to chasing this signal, gave it a name in 1976, Geminga, a playful fusion of Gemini and Gamma, and, in Bignami's own Milanese dialect, a pun meaning "it's not there." Few names in astronomy have ever been more fitting for an object that spent decades refusing to reveal itself. The next breakthrough arrived in 1983, when Bignami's team detected a faint X-ray signal using the Einstein X-ray satellite, narrowing the search area further without yet answering the fundamental question of what Geminga actually was. That answer finally arrived in 1991, when 2 separate missions caught the source pulsing rather than glowing steadily. Having seen fame, the German-built Rosat satellite detected pulses in the X-ray band, and shortly afterward, NASA's Egret telescope, riding aboard the Compton Gamma Ray Observatory, confirmed matching pulses in gamma rays. The rhythm repeated every 0.237 seconds, a little over 4 flashes per second, and that steady heartbeat told astronomers exactly what kind of object they had found: a pulsar. A pulsar is the ultra-dense remnant of a massive star, spinning rapidly and sweeping beams of radiation across space like a lighthouse. From Earth's perspective, most known pulsars flash anywhere from a few times a minute to hundreds of times per second. And in gamma rays, Geminga was only the third such pulsar ever confirmed. The first two, the Crab and Vela pulsars, both emitted strong radio waves as well as gamma rays, and both sat visibly nestled inside glowing nebulae, the leftover debris clouds from the supernova explosions that created them. Gamma ray broke both patterns. It showed no obvious radio emission whatsoever, making it apparently the first radio-silent gamma-ray pulsar ever discovered. And it appeared to have no surrounding nebula at all, a conspicuous absence for an object born from a supernova. A pulsar hiding its radio signal and hiding its own birth debris. Two mysteries wrapped inside one very stubborn dead star. The explanation for Geminga's apparent radio silence turned out to be embarrassingly human. Radio pulsars can technically emit across an enormous range of frequencies, from as low as 17 megahertz up past 87 gigahertz, covering roughly half the entire radio spectrum. But not every frequency survives the journey through interstellar space equally well. The interstellar medium, background sky temperature, and interference from Earth's own ionosphere all conspire to weaken lower frequency signals dramatically by the time they reach us. Even though pulsars are often intrinsically brightest somewhere between 100 and 200 megahertz. Because those weak low-frequency signals are so difficult to detect, most radio telescopes of the era had simply never bothered searching that range, focusing instead between 430 and 1600 megahertz, where signals arrive far stronger. Had Geminga behaved the way most pulsars do, this shortcut would never have mattered. Since it didn't, it took until 1997 for 3 independent observations from the Pushchino Radio Astronomy Observatory, using an especially sensitive antenna, to finally catch extraordinarily faint pulses from Geminga hovering right around 100 megahertz. The star had never actually been silent. Astronomers had simply been listening in the wrong place. That same year, a team led by the late astronomer Janusz Gill proposed a second contributing factor. Geminga's own magnetic field, they theorized, might be absorbing or refracting much of its radio output within the pulsar's magnetosphere before it ever escaped into space, leaving only the faintest trace detectable at the lowest frequencies. Between weak intrinsic output and decades of searching in the wrong frequency range, Geminga had managed to hide in plain sight for a quarter of a century. Confirming its identity as a genuine gamma-ray pulsar carried real weight. 99% of Geminga's entire energy output radiates as gamma rays, making it one of the brightest gamma-ray sources in the entire Milky Way. What remained of the original star that exploded roughly 350,000 years ago now measures only 20 to 30 kilometers across, yet packs in about 1.5 times the mass of our Sun. A teaspoon of its material would weigh around 4 billion tons, equivalent to 10,000 Empire State Buildings compressed into a spoonful. Its missing radio signal had finally been found. Its missing nebula would take considerably longer to explain. While chasing Geminga's missing nebula, Italian astrophysicists, including Bignami, compared observations from the European Southern Observatory's 3.6-meter telescope, its New Technology Telescope, and the Canada-France-Hawaii Telescope. What they found added yet another layer to the mystery. Geminga was moving, and moving fast, drifting across the sky at roughly 0.22 arcseconds per year. An arcsecond is a tiny sliver of angular measurement, 1/3600th of a single degree. Hold your little finger at arm's length against the night sky, and it covers roughly 1 full degree, more than enough to hide the entire moon, which itself spans only about half a degree or 31 arc minutes from our point of view. Most stars drift across our sky at only a few thousandths of an arcsecond per year, essentially motionless on any human timescale. Geminga, despite sitting 800 light-years away, will cover the equivalent of the moon's full width across our sky in just over 10,000 years, moving at a genuinely blistering pace of roughly 210 kilometers per second. At that speed, Geminga is currently racing toward the border between the constellations Gemini and Lynx, and will remain within Gemini for approximately another 500,000 years against the camera, and constantly chase the camera against fever. It may well need a new name by then, assuming anyone is still using the same naming conventions 500,000 years from now. This tremendous velocity turned out to hold the key to explaining Geminga's second missing feature. As it plows through the thin gas and dust of interstellar space, its motion generates a shockwave, compressing the surrounding material and its embedded magnetic field by a factor of roughly 4. In 1999, the European Space Agency launched the XMM-Newton X-ray telescope specifically to study exactly this kind of high-energy environment. And 4 years later, a team led by Patrizia Caraveo used it to uncover 2 ghostly X-ray tails trailing behind Geminga, stretching an almost incomprehensible 3 trillion kilometers across the sky. Picture a speedboat cutting across still water, throwing a V-shaped wake behind it that stretches far longer than the boat itself. Geminga produces something remarkably similar, except its wake is not made of water, but of high-energy electrons and their antimatter counterparts, accelerated to extreme speeds by the pulsar's relentless spin and intense magnetic field. Some of these particles escape entirely as gamma radiation. Others become trapped, spiraling within the compressed magnetic field generated by Geminga's forward motion, forming the twin X-ray tails that stretch trillions of kilometers along the edges of its three-dimensional shockwave. The final missing piece of the puzzle, the nebula that had eluded astronomers for over 3 decades, finally appeared in 2005. It took the shape of a shell of neutral hydrogen gas spanning roughly 0.4 parsecs, a structure astronomers classify as a pulsar wind nebula. Formed not from supernova debris in the traditional sense, but from charged plasma streaming outward from the pulsar's magnetic poles, accelerated to nearly the speed of light and glowing brightly in X-rays as it collided with surrounding material. With that discovery, Geminga's identity was finally locked in beyond doubt, but the Chandra X-ray Observatory offered one more revelation by comparing Geminga directly against a second, remarkably similar pulsar known as B0355+54. Both objects are roughly 500,000 years old. Both spin at nearly identical rates, somewhere between 4 and 5 times per second. Yet Geminga shines primarily in gamma rays, while remaining almost invisible in radio, and pulsar B does the exact opposite, blazing brightly in radio while staying essentially dark in gamma rays. The explanation turned out to hinge entirely on orientation. Both pulsars, like Earth, have magnetic poles positioned close to their spin axes, and radio emissions beam outward from those poles like a skewer poked straight through a spinning foam ball. Gamma ray emissions, by contrast, radiate outward along the spin equator, more like a flat paper plate wrapped around the middle of that same ball. With Geminga, the edge of that imaginary plate happens to point directly toward Earth, sending its gamma rays our way, while its radio beams, running perpendicular, sweep off to the sides and miss us entirely. Pulsar B sits oriented the opposite way, aiming its radio beam squarely at Earth, while its gamma ray equator points elsewhere. Two nearly identical dead stars, viewed from two different angles, producing two completely different signatures. Sometimes the universe's greatest mysteries resolve into something as simple as geometry. To appreciate exactly how strange Geminga's behavior was in 1991, it helps to place it side by side with the two pulsars astronomers already knew intimately, Crab and Vela, both discovered decades earlier, and both, in very different ways, considered the gold standard of what a young gamma-ray-emitting pulsar was supposed to look like. The Crab pulsar sits at the heart of the Crab Nebula, the glowing debris cloud left behind by a supernova that Chinese and Arab astronomers recorded observing in the year 1005, nearly 1,000 years before telescopes existed to study it properly. Spinning roughly 30 times per second, considerably faster than Geminga's 4, the Crab pulsar remains one of the most energetic and well-studied objects in the sky. Visible not just in gamma rays and radio waves, but across almost the entire electromagnetic spectrum, from X-rays down to visible light. Its nebula glows so brightly that it was one of the first deep sky objects ever catalogued, appearing as the very first entry in Charles Messier's famous 18th century catalogue of celestial objects. Vela, discovered in 1968 in the southern constellation of the same name, spins slightly slower than Crab at around 11 times per second, and its supernova remnant, while fainter than the Crab Nebula, remains clearly visible in X-ray and optical observations, sprawling across a region of sky roughly 8 degrees wide. Vela earned particular fame among physicists for exhibiting sudden, unexplained jumps in its rotation speed, glitches that offered scientists their first real observational window into the internal structure of neutron stars, revealing that these ultra-dense objects likely contain a superfluid core capable of briefly transferring momentum to the outer crust in sudden, violent events. Set against these two benchmarks, Geminga's profile looked almost deliberately contrarian. No visible nebula for over 3 decades, where both Crab and Vela wore theirs proudly and visibly. No detectable radio emission for a quarter of a century, where both Crab and Vela had been reliable radio sources since their discovery. And many, a rotation speed roughly 7 times slower than Crab and nearly 3 times slower than Vela, suggesting Geminga was considerably older and had already bled off much of its initial rotational energy through the exact same gamma-ray and particle emission processes this documentary has spent so much time exploring. That comparison ultimately became the key to unlocking Geminga's mysteries rather than deepening them. Where Crab and Vela demonstrated what a young, energetic, favorably oriented pulsar looks like, Geminga demonstrated what an older, still energetic pulsar looks like when viewed from an unfavorable angle. Its radio beams sweeping harmlessly past Earth, while its broad gamma-ray equator happened to point directly at us. The legends taught astronomers what to expect. Geminga taught them what happens when a pulsar refuses to cooperate with those expectations, and in doing so, quietly rewrote the rulebook for how many hidden gamma-ray pulsars might still be waiting undiscovered throughout the galaxy. Simply pointed the wrong way for their radio signals to ever reach us. Stepping back from Geminga specifically, it helps to understand why pulsars behave the way they do at all, because the physics involved is almost as strange as the antimatter it produces. A pulsar is born the moment a massive star, typically somewhere between 8 and 25 times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity. The outer layers explode outward in a supernova, scattering heavy elements across space, while the core collapses inward with such force that protons and electrons are crushed together into neutrons, forming an object with the mass of a sun packed into a sphere barely wider than a city. That collapse comes with two dramatic side effects, both a direct consequence of preserving quantities that physics insists must be conserved. Angular momentum, the same property that makes a spinning ice skater speed up dramatically when pulling their arms inward, forces the collapsing core to spin faster and faster as it shrinks. A star that once rotated lazily once every few weeks can emerge from collapse spinning hundreds of times per second. A transformation roughly equivalent to an entire city block, condensing down to the size of a coin, while somehow spinning fast enough to blur. Magnetic field lines undergo a nearly identical squeeze. Conservation of magnetic flux means that as the star's surface area shrinks by a factor of billions, its magnetic field strength increases by a comparable amount, producing surface fields on a typical pulsar trillions of times stronger than anything achievable in an Earth-based laboratory. Combine an object spinning hundreds of times per second with a magnetic field of that ferocity, and you get a natural particle accelerator far more powerful than anything humans have ever constructed, ripping charged particles directly off the neutron star's surface and flinging them outward at velocities approaching the speed of light. This is precisely the mechanism responsible for producing positrons in such enormous quantities. The same intense electromagnetic environment that generates a pulsar's beamed radio and gamma ray emissions also happens to be phenomenally efficient at creating electron-positron pairs directly out of pure energy, a real-world demonstration of Einstein's mass-energy equivalence running in reverse from our earlier meteor calculation. Rather than converting mass into energy through annihilation, a pulsar's magnetosphere converts energy back into matter and antimatter in equal measure, manufacturing the very substance our entire story has been chasing. Not as a rare cosmic accident, but as a routine, ongoing byproduct of simply being a neutron star. Multiply that process across the roughly 300 confirmed gamma-ray pulsars scattered throughout our galaxy, and the natural antimatter factory hiding in plain sight starts to look considerably larger than anyone suspected before. Geminga forced the question. For more than a decade, a particle detector called the Alpha Magnetic Spectrometer has ridden aboard the International Space Station, quietly cataloging cosmic rays, dark matter candidates, and antimatter particles raining down from space. In 2013, its first major results landed with considerable fanfare. Over 400,000 positrons detected, the largest sample of cosmic ray positron data ever assembled, increasing the world's total positron database roughly 100-fold in a single announcement. The excitement rippled through the astrophysics community for a specific reason. Dark matter, the invisible substance believed to make up around 27% of everything in the universe, while stubbornly refusing to interact with light in any detectable way, had long been theorized to occasionally annihilate with itself, producing exactly this kind of positron signature as a byproduct. If the excess antimatter detected by the space station really came from dark matter annihilation, it would represent one of the most significant breakthroughs in modern physics, finally offering a concrete clue about a substance that has eluded direct detection for nearly a century. The deeper scientists dug into the data, though, the less that explanation held up. A far more mundane suspect kept surfacing instead: pulsars. Astrophysicists had suspected pulsars as a possible source for years, but concrete proof remained elusive until 2017. when the high-altitude Water-Cherenkov Observatory detected a halo of extraordinarily energetic gamma radiation surrounding Geminga itself, carrying between 5 and 40 trillion electron volts, precisely the signature expected from accelerated positrons colliding with ambient starlight. Pulsars naturally generate halos of electrons and positrons thanks to their intense magnetic fields, which rip charged particles straight off the star's surface and accelerate them to speeds approaching light itself. Those particles collide with surrounding starlight, boosting it to extreme energies that radiate outward as the observed gamma-ray glow. Based on the size of the halo detected, though, the observatory's team concluded that Geminga's positrons would rarely retain enough energy to travel the full 800 light-years to Earth, suggesting the excess detected aboard the space station still needed a more exotic explanation. That conclusion didn't survive long. Before pulsars emerged as the leading explanation for the positron excess, dark matter hunters had already spent decades chasing an entirely different family of suspects. And understanding why those searches came up empty helps explain why the positron excess felt so tantalizing when it first appeared. From much of the late 20th century, the leading dark matter candidate was a hypothetical particle class known as WIMPs, or weakly interacting massive particles. Theorized to interact with ordinary matter only through gravity and the weak nuclear force, making them exceptionally difficult to detect directly, but appealingly consistent with independent predictions coming out of certain extensions to the standard model, particularly a framework called supersymmetry. Massive underground detectors, shielded from cosmic ray interference by kilometers of solid rock, were built specifically to catch the extraordinarily rare event of a WIMP colliding directly with an atomic nucleus. Facilities like Lux in South Dakota and Xenon in Italy's Gran Sasso Mountain Laboratory ran for years watching vats of ultra-pure liquid xenon for the faintest possible flicker of light that a WIMP collision might produce. None of them ever found one. Successive generations of these detectors grew more sensitive by orders of magnitude with each iteration, ruling out larger and larger swaths of the theoretical parameter space where WIMPs were predicted to hide, without ever producing the positive detection the field had hoped for. By the 2010s, confidence in the simplest WIMP models had eroded considerably, not because the underlying idea was disproven outright, but because the most natural, most theoretically favored versions of it had been searched for exhaustively and found wanting. Against that backdrop of repeated null results, the alpha magnetic spectrometer's positron excess arrived like a lifeline. Certain dark matter annihilation models predicted exactly this kind of signature, an unexpected surplus of positrons at high energies, produced when two dark matter particles collided and destroyed each other, converting mass into ordinary and antimatter particle pairs, in a process conceptually similar to the annihilation events driving everything else in this documentary. For a brief window, the positron excess represented one of the most promising indirect dark matter signals the field had ever produced. Discussed seriously at conferences and cited in hundreds of theoretical papers exploring exactly which dark matter model might explain the observed energy spectrum. Pulsars becoming the accepted explanation instead did not diminish the importance of that earlier excitement. Ruling out an explanation, especially one this carefully studied, still counts as genuine scientific progress, narrowing the search and forcing theorists back to the drawing board with better constraints than they had before. Dark matter remains exactly as mysterious today as it was before AMS-02 launched, still comprising roughly 27% of the universe, still refusing to interact with light in any detectable way, still waiting for its own version of a Geminga moment, an unexpected signal from an unexpected direction that finally cracks the case open. A team led by astrophysicist Mattia De Moro revisited the question using an entirely different dataset, an entire decade of gamma-ray observations collected by the Fermi Large Area Telescope, an instrument capable of detecting lower energy light than the earlier Walter Cherenkov Observatory had been sensitive to. By carefully subtracting out every other known gamma-ray source cluttering the surrounding sky, De Moro's team uncovered something nobody had previously seen: a vastly larger glow surrounding Geminga than anyone had suspected existed. At an energy of 10 billion electron volts, the newly revealed halo stretched across 20 degrees of sky, roughly the same visual footprint as the Big Dipper constellation. At lower energies, the glow expanded even further. Were human eyes sensitive enough to perceive it directly, Geminga's gamma-ray halo would dominate the night sky entirely, spanning an area 40 times larger than a full moon. Suddenly, the earlier conclusion that Geminga's positrons couldn't reach Earth needed serious revision. With a halo this enormous, the pulsar alone could plausibly account for as much as 20% of the excess positrons detected bombarding our planet. A staggering contribution from a single dead star 800 light-years away. Extend that logic across the roughly 300 gamma-ray pulsars discovered throughout the galaxy since Jocelyn Bell first identified pulsars altogether back in 1967. And pulsars collectively emerge as the most plausible explanation for essentially the entire cosmic positron excess. The dark matter mystery remains unsolved, no closer to an answer than it was before the space station's detector switched on. But in its place sits an equally remarkable discovery. Somewhere in the sky above Gemini, a dead star, smaller than a city, has been quietly manufacturing antimatter for over 350,000 years, streaming it silently across the galaxy in numbers vast enough to rain down on planets it will never come close to visiting. No conversation about antimatter feels complete without addressing the elephant sitting quietly in the corner of every science fiction franchise ever made. Antimatter annihilation converts 100% of mass directly into energy, dwarfing the efficiency of every other known fuel source by an enormous margin. Chemical rocket fuel converts roughly 1/10 billionth of its mass into usable energy. Nuclear fission, the process powering both reactors and atomic weapons, manages perhaps 1/10 of 1%. Antimatter annihilation manages the full 100%, every single time, with no exceptions and no wasted byproduct. On paper, this makes antimatter the single most efficient fuel physics allows, and it is precisely why science fiction has spent decades imagining warp drives and interstellar engines running on the stuff. In practice, the obstacles standing between that dream and reality are almost comically enormous. CERN currently produces antimatter at a rate and cost that would make a single gram, roughly the mass of a paperclip, cost trillions of dollars and take longer than the current age of the universe to manufacture using existing accelerator technology. NASA has estimated that producing just 1 milligram, a fraction so small it would be difficult to see with the naked eye, would cost tens of billions of dollars using current methods. Storage presents an equally daunting challenge. Antimatter cannot touch any container made of ordinary matter without annihilating instantly, meaning any practical storage system requires suspending it in a magnetic or electric field, floating and completely isolated from any physical surface. The same fundamental technique used inside CERN's Alpha experiment to trap anti-hydrogen atoms for measurement. Scaling that delicate containment method up from a handful of individual atoms to a fuel tank capable of powering a spacecraft remains, to put it generously, a problem for a much more advanced civilization than our current one. None of this means the dream is permanently dead. Small-scale antimatter-catalyzed propulsion concepts have been seriously studied by NASA-funded researchers, envisioning designs where a tiny quantity of antimatter, measured in micrograms rather than tons, triggers and boosts a conventional nuclear fission or fusion reaction, rather than serving as the primary fuel source itself. These hybrid designs could theoretically enable spacecraft to reach outer planets in a fraction of current travel times, using antimatter as a catalyst rather than a bulk propellant, sidestepping the worst of the production and storage problems while still capturing some of the efficiency gains. For now, though, every gram of antimatter humanity has ever produced across the entire history of particle physics, combined from every experiment at every laboratory on the planet, would not be enough to boil a single cup of tea if fully annihilated. The most efficient fuel physics allows remains, for the foreseeable future, entirely theoretical, outside of a laboratory setting, which makes it all the more remarkable that nature appears to be manufacturing it constantly in enormous quantities, entirely for free, inside dead stars like Geminga that we only stumbled upon by accident. A few questions tend to surface every time this subject comes up, so let's address them directly before closing this out. Could an antimatter meteor be heading toward us right now without our knowledge? Based on everything covered here, almost certainly not. The interstellar journey required to reach us intact demands a survival window far longer than physics allows for an object of meteor scale, and no telltale gamma-ray trail, the kind that would betray such an object's approach at interstellar distances, has ever been observed anywhere near our solar system. Has anyone ever proposed that a historical impact crater was actually caused by antimatter? Yes, informally, largely in the decades immediately following Tunguska, when the concept of antimatter was new enough that scientists were still mapping out which observations it could and couldn't explain. No confirmed impact crater on Earth has ever required an antimatter explanation once conventional geology and chemistry were applied, and every crater studied in detail has turned up physical evidence, embedded metal fragments, shock-altered minerals, or telltale chemical signatures consistent with an ordinary rocky or icy impactor. Why does any of this matter if the danger is essentially theoretical? Because the search for antimatter, in every form discussed across this documentary, from anti-stars to CERN's gravity experiments to Geminga's positron factory, has repeatedly produced real, verified, non-theoretical discoveries, even when the original terrifying premise didn't pan out. Nobody found dinosaur-killing antimatter asteroids, but the search led directly to precision tests of general relativity, a deeper understanding of pulsar physics, and the eventual explanation for a genuine cosmic ray mystery that had puzzled astrophysicists for over a decade. Chasing the extreme, even when the extreme scenario turns out to be unlikely, has a well-documented habit of uncovering something real and valuable along the way. Is there any realistic timeline for resolving the baryon asymmetry mystery? Physicists are cautiously optimistic, but refuse to commit to a firm date. Upcoming upgrades to CERN's accelerator complex, new neutrino experiments designed to search for charge parity violation in an entirely different particle family, and next-generation gravitational wave detectors capable of probing the earliest fractions of a second after the Big Bang, all represent live avenues of investigation. Any one of them could, in principle, turn up the missing piece within the next decade. Equally, the mystery could persist for another century. Sakharov handed physicists a checklist in 1967, and the honest truth is that nobody currently knows how many items remain before it's finally complete. Every pulsar in this story, Geminga included, traces its scientific lineage back to a single discovery made in 1967 by a 24-year-old graduate student named Jocelyn Bell. working alongside her supervisor, Anthony Hewish, at Cambridge University. Bell had spent months painstakingly building and operating a radio telescope array designed to study quasars, sifting by hand through roughly 96 feet of chart paper produced by the instrument every single night, searching for scintillating radio sources. Buried within that mountain of paper, Bell noticed something the instrument wasn't supposed to be capable of finding: an impossibly regular pulse, repeating with clockwork precision every 1,337 seconds. Far too fast and far too consistent to match any known astronomical phenomenon. For a brief, genuinely thrilling period, the team half-jokingly labeled the signal LGM-1, short for Little Green Men, entertaining the possibility, however unlikely, that they had stumbled onto an artificial signal from an extraterrestrial civilization. Bell herself later downplayed how seriously the team actually considered that explanation, but the label stuck around long enough to make it into the history books. Further observations soon revealed additional pulsing sources scattered across different parts of the sky, each with its own distinct, precise rhythm, effectively ruling out any single artificial or extraterrestrial origin and pointing instead toward a natural astrophysical explanation: rapidly rotating neutron stars, sweeping narrow beams of radio emission across space, exactly the way a lighthouse sweeps its beam across a coastline. The discovery of pulsars earned Hewish a share of the 1974 Nobel Prize in Physics, awarded jointly with fellow radio astronomer Martin Ryle. Bell, the graduate student who had actually spotted the signal buried in the chart paper, was left off the prize entirely, a decision that remains one of the most widely debated omissions in the history of the Nobel Committee. Bell herself responded to the snub with remarkable equanimity over the following decades, arguing publicly that Nobel Prizes are typically reserved for the senior researcher directing a project, rather than the student carrying out the observational work, while simultaneously becoming one of the most respected figures in astrophysics through her later research and mentorship. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million, and immediately donated the entire sum to fund graduate scholarships for women, minorities, and refugees pursuing careers in physics, a gesture widely seen as both graceful and pointed. Every pulsar discussed across this documentary, Crab, Valea, Geminga, and the roughly 3,000 others now catalogued across the galaxy, exists as a recognized category of object, specifically because a 24-year-old student refused to dismiss an anomaly buried in 96 feet of chart paper as mere instrument noise. Sometimes the biggest discoveries in astrophysics come not from the most powerful telescope in the world, but from the person patient enough to actually read every single page the telescope produces. Step back and look at the full shape of this story, and a strange pattern emerges. We began with the terrifying possibility of an antimatter meteor, a grand piano-sized object capable of erasing a state, and worked our way down to a reassuring conclusion. Such a meteor, if it exists at all, almost certainly cannot survive the journey to reach us. Then we turned to CERN's most delicate experiments, confirming that gravity, at least, treats matter and antimatter exactly the same, closing off one of the few doors that might have explained why the universe favors one substance so overwhelmingly over the other. And then, almost as if the universe wanted to remind us that antimatter is not confined to bombs and hypotheticals, we found it quietly streaming from a source that had been hiding in plain sight since 1972. A dead star that took 25 years just to reveal that it was speaking to us at all, and another decade after that to reveal how loudly. Every dead end in this story taught us something real. The weak force treats matter and antimatter slightly differently. but not nearly enough to explain a universe built almost entirely of one over the other. The strong force treats them identically. Gravity treats them identically. And yet somewhere, in a fraction of a second after the Big Bang, some rule we still don't understand tipped the scales by one particle in a billion. And that single tip is the entire reason there is a universe left to study at all. Geminga did not solve that mystery. It never claimed to. What it did was remind an entire field of scientists that antimatter isn't a laboratory curiosity confined to particle accelerators and speculative doomsday scenarios. It streams naturally through the galaxy in enormous quantities, manufactured by dead stars spinning faster than most machines humans have ever built, hidden from view simply because we were listening at the wrong frequency and looking in the wrong energy range. Perhaps that is the real lesson sitting underneath all the math and all the acronyms. The universe rarely hides its secrets out of malice. It hides them because we haven't yet learned to listen in the right place, at the right frequency, with the right instrument pointed in the right direction. Geminga was never actually gone. It was there the entire time, exactly where its name insisted it wasn't, patiently waiting for someone to finally tune in. Somewhere out there, 40,000 tracked objects drift through the space around Earth, and in all likelihood, not a single one of them is built from antimatter. But 300 gamma-ray pulsars, now confirmed across our galaxy, are still out there spinning, still manufacturing positrons by the trillions, still sending pieces of the universe's oldest unsolved mystery streaming silently past our planet every single day. We simply had to learn how to see them. Think back, for a moment, to that opening image. A piece of furniture-sized debris falling silently out of a clear sky, carrying enough energy to erase a state. It was never really a prediction. It was a thought experiment, built to make an abstract idea feel physical. The same way a stadium and a marble once helped make sense an atom too small to picture, or a handful of sand once helped make sense of a universe too large to count. That is what good physics communication has always tried to do. Take something genuinely incomprehensible and hand you just enough of a handle to carry it around in your head for a while. The real takeaway was never the piano, or Texas, or even the number itself. It was the pattern sitting quietly underneath every section of this story. Every time humanity assumed a corner of the universe was empty, silent, or settled, closer inspection revealed something manufacturing exactly the substance we thought was missing. Earth's own magnetosphere quietly stockpiles antiprotons. A supposedly ordinary neutron star turned out to be one of the galaxy's most productive positron factories. A gravitational question left unanswered for 80 years turned out to have a definitive answer waiting the moment somebody built an instrument delicate enough to ask it properly. None of this closes the case on why the universe favors matter over antimatter by that impossibly narrow margin of 1 part in a billion. If anything, every experiment covered here narrowed the list of easy answers and widened the list of genuine mysteries. The weak force cracked open a door too small to matter. Gravity slammed its door shut entirely, confirming symmetry rather than breaking it. And a dead star spinning 4 times a second, 800 light years from where you're sitting right now, turned out to be steadily manufacturing more raw antimatter than every particle accelerator on Earth combined, doing so for free. For over 300,000 years, without a single physicist noticing until 1972, and without anyone fully appreciating the scale of it until 2020. That gap between when a signal first arrives and when we finally understand what it means, might be the most human part of this entire story. Geminga's gamma rays had already been washing over Earth for hundreds of thousands of years before Big Nami gave the source its fittingly evasive name. The antiprotons circling quietly in our own Van Allen belts had been forming and vanishing for as long as Earth has had an atmosphere and a magnetic field, waiting patiently for a satellite capable of noticing them. The universe rarely announces its secrets loudly. More often, it leaves them sitting in plain sight at the wrong frequency, in the wrong energy band, disguised as noise, until someone finally builds an instrument sensitive enough or asks a question specific enough to hear what was there all along. So the next time you look up at Gemini on a clear night, remember that somewhere within that quiet constellation, invisible to your eyes and largely invisible to your imagination, a dead star, smaller than a city, is still spinning. Still glowing brighter in gamma rays than almost anything else in the galaxy. Still streaming antimatter across a halo 40 times wider than the full moon. It has been doing this the entire time you have been alive, the entire time your parents were alive, the entire 350,000 years since the star that made it first exploded. We only just started listening. And if the last century of antimatter physics has taught us anything at all, it's that the universe is very rarely as empty, as quiet, or as settled as it first appears. We simply have to keep building better ways to look.